Swayam Prabha. Digital India. Educated India.
Welcome back. We're going to talk a little bit more about oxidations of alcohols. We talked a little bit about how you can use Jones oxidation, which is basically dichromate and sulfuric acid, and they oxidize secondary to ketone. Let's look at what happens with the primary. This pretty much the same thing happens with the primary alcohol. So I'm going to put this is your second reaction on that. So let's say you have a primary alcohol, so two hydrogens here. We talked about how primary is 2, secondary is 1, and tertiary is none. So let's say you have this, we'll do the same thing here, CrO. This is your nucleophile. This is electron deficient because it's getting pulled in all directions by those oxygens. So it goes right over there, pops up one of those pi bonds, and you will get an oxygen that links to a chromium. So it's got an even better leaving group than before. Very good leaving group here, chromium. And you have an O minus oxygen, and this minus, when it's rotating, it can get right close to that hydrogen that's very, very acidic. pKa is about -2 for that, and that's going to pull that off. And so here's your oxygen now with a chromium trioxide hanging off of it. This is in an acid medium, so it's fine to have protonated oxygens here. So here's your chromium with your OH, double bond O and double bond O. And well, this is going to be a good leaving group. All you have to do is give it a pair of electrons and it'll say, bye, I'm on my way. So you can take this molecule, or you can take a water molecule, because water is a weak base. It can deprotonate that and give those electrons to the chromium. It's going to get protonated instantly, but it's going to be a little crowded to write everything here, so we will do this. And now you only have one hydrogen, and this is your aldehyde. Now, does it stop here? There's another hydrogen. These are very, very powerful oxidizing agents, so it's going to oxidize that again. So we are not going to stop there. So aldehyde is really kind of an intermediate molecule here. So the O minus here, you can protonate that with, let's say, the acid. We have a ton of acids in there, and you will get HOOH. You protonate that, and you will get a chromic acid that is a lot less powerful than your original molecule, H2CrO3. So that is kind of done, but we'll have more chromic acid in the solution that will then oxidize this molecule further. It's again going to do the same thing. The oxygen is going to hold on to a chromium. Water molecule adds here, and then it picks up this hydrogen and oxidizes it again. And so now you're going to oxidize this further to a carboxylic acid. So I'm just going to put oxidation further to a carboxylic acid. So that's for primary. We will never stop at aldehyde here. So you'll go from primary to aldehyde, and aldehyde to carboxylic acid, all the way there. What if you don't want to go all the way? You want to stop here. Well, then you don't want such a powerful oxidizing agent. What we do is you kind of add HCl to this and make it a little less oxidizing. So let's say I have a primary, so I say to stop at aldehyde from primary. Because secondary can only go to ketone. There's no choice there. But aldehydes have choices. They can go all the way to carboxylic acid or stop here. So let's say I have a primary alcohol here, and I am going to use this to just stop right here at an aldehyde. So I will pump chloride into this pyridinium chloride. So here I'll take this, and if I pump a chloride into this, let's say I have this, and I put in a chloride minus, that's going to bond to this and make this into an anion. So now that is called pyridinium because you have a counter ion there, HCl. So the pyridine catches the hydrogen and the chloride then attacks the chromium trioxide and you get PCC. This is pyridinium chromochloride, PCC. So this molecule is not as powerful as that, and let's see what happens. And you put just enough to do this reaction. So you take this and again, same thing. This is your nucleophile, this is very electronegative, so it's going to pop this off. Now, this is in a basic medium, so it's fine to have anions here. So here, you are going to have that oxygen now linking to that chromium, making it a good leaving group. That's the whole purpose because we want to take off the hydrogen and kick off a leaving group. So here, you will have chromium opened up, you have two O minuses, a double bond, and a chlorine, and you can see how crowded this can get. Chlorine's got 3 lone pairs, oxygen's got 3 lone pairs. I mean, this is just really butting heads. So one of the oxygen says, hey, chloride, you know what, it's time for you to leave. So the chloride leaves, and you can also deprotonate that right away, but I can do it here now. So you have 1 oxygen minus here on the chromium, and that can come back and deprotonate that hydrogen because that's pretty acidic. pKa is like -2, and as we said earlier, when this protonates, that's pKa 6.9, so it's going to be a good way to get rid of that hydrogen. So that's going to deprotonate that. I mean, if you have water, you can do the same thing. We have this guy all set to do a nice elimination. So here is your hydrogen, and here is your chromium, and your chromium can have these oxygens here that are very oxidizing, and that's going to do the job. So the oxygen is going to catch that hydrogen, and that's going to take those electrons, put it on the oxygen, which will then give it to the chromium. So we have a very nice setup there with a good leaving group. So you have this going over now to a pi bond right there. Now your chromium double bonds are pretty much all used up, and so it's not powerful enough to go and do this again. So therefore the reaction stops there. That's where the buck stops, as you say. So you have H2CrO3, and I'll just put a note. This is not powerful enough to oxidize aldehyde to acid. So that's the main difference. This is called PCC oxidation, and this is Jones oxidation with K2Cr2O7 and H2SO4. That's called Jones, and this is called PCC. So we got 2 different ways of oxidizing. Now, some of the time, even this might be a little too reactive. So we have another milder, gentler one that's called Swern. So let's do a Swern oxidation. So what would happen if this had been a ketone? Let's say I took a ketone and did this and put PCC. You only have 1 hydrogen. So that hydrogen would get pulled off, and there's an R group here. So there'll be an R group here, and it'll be a ketone. So if you have a secondary alcohol with PCC, which is the same thing as this, you would stop right here. You would stop right here. Secondary will give you ketone. Primary with PCC will give you aldehyde, and we just saw that. Right. So that's something to remember. So let's see what another way of taking a primary and stopping at an aldehyde, and that's called a Swern oxidation. In a Swern oxidation, you are going to use DMSO as your solvent. Oxalyl chloride, COOCl. And you'll also have a base, NET3. So these are the three things that you're going to use, and you will do a primary alcohol to a aldehyde or secondary to ketone. This is something we can do with pretty much Jones, PCC, and so on. So this is the one that's most sensitive. So this is mainly used for primary to go to aldehyde. So let's look at this. All right, so first we have to prepare a certain molecule that then attacks the alcohol. So let's prepare that. Take DMSO, dimethyl sulfoxide. Dimethyl sulfoxide, has a resonance form. Let's draw that out. Well, let's say for a moment it goes to this resonance form, plus minus. This can attack one of these carbonyls here. Just pretty much making it a good leaving group. So here is our oxalyl chloride, oxalic acid. So the OHs are now converted to chloride. So it's oxalyl chloride. Attacks that, opens that up. You cannot do an SN2 because it's an sp2. So we have to literally open this up. You can't, it's very tempting to just say chlorine is going to leave. But because it's sp2, we have to draw it out like this. Oxygen now bonded to a carbon, chlorine minus, oxygen minus, and then when you have too many lone pairs on the same carbon, they'll fight it out for space, and one of them's going to get kicked out. In this case, the chlorine is going to get kicked out. All of this. So here is your sulfur now with a carbonyl. So this is an ester, a really good electronegative leaving group. And so now you have this positive. Now this leaving group needs something to come and give it a good kick on the back for it to leave, like an SN2. And so that's what happened. This comes over here, kicks out your oxygen there. That is going to come over, well, if you look at it, this is carbon dioxide, which of course it wants to leave. And so that's going to then go over here and kick out a chlorine. So all of this just to prepare a very nice molecule to oxidize your alcohol. So here we have CH3 sulfur. I'm going to draw the chlorine up where the oxygen was. And sulfur has got CH3. There you go. So you would have here 1, 2, 3, 4, 5. 6 minus 5 is going to be a +1 oxidation formal charge. Plus a lot of the side products like CO2 is going to be a gas. Carbon monoxide is going to be a gas. So lots of gases coming out. There's a lot of good entropy that will drive this reaction forward. So now you can take this and oxidize the primary to an aldehyde or the secondary to a ketone. This is our important guy here. All of this was just to prepare the material to oxidize. Now in walks in your alcohol. It's no idea what's going to happen in over here. So then as soon as it comes in, well, the sulfur is positive. Sulfur and oxygen are same group. They're good friends. And says, so oxygen's like, hey, come over here. Let's get this chlorine guy out of the way. So the chlorine is anyway itching to leave with an octet. So the oxygen comes in and bam, does an SN2 type of reaction, kicks out your chlorine. Now you have, well, any kind of primary. I'll just put in oxygen there. And here's your hydrogen. You lost a lone pair, you're positive, but no worries. We got plenty of friends there to take care of that. So your chloride's gone. You have SCH3 here and the chloride coming off. Now chloride is actually neutral. So you don't want to use chloride to remove that. Chloride's a conjugate base of a strong acid. They're neutral. by definition. So you're going to use this other guy, like the spider guy, okay, which is just a nice, beautiful base, nitrogen base. It cannot do SN2 because it's too crowded. See, that's why we make it bulky, so it doesn't do SN2 and take over your beautiful reagent there. So therefore, we're making a bulky base that cannot do SN2. That's going to pull that off. And now you can see how, this guy, this DMSO guy is you got both your lone pairs back, and here's your sulfur, CH3, CH3. There's a reason I'm writing it out, because the nitrogen can take this off as well, because it's next to an electronegative group. So the nitrogen is next going to come in. It's looking for acidic protons. There's one here. There's one next to the hydrogen here. Well, they found out it actually goes for this. The spider comes back and gets this guy. And it can go over to the sulfur and make a double bond. I'm just going to draw one of the resonance structures for that. Probably going to be in the double bond there, but some of the time it's going to be in an anion form. They can rotate, so at some point this is going to be a double bond here, and then draw the resonance structure for that. So this is probably going to be a better resonance structure, but at some point you can draw both the resonance. So this is the resonance structure for that, which is just the oxygen and the sulfur here, well, going back and forth here, CH2 minus, plus on the sulfur, and this is just a resonance structure. It's probably going to prefer this because the charge is a lot less, but at some point there is a chance that it's going to also do this. And sulfur, is period 3, it can have more than 8 electrons. Now this guy is all set 1, 2, 3, 4, 5. So that's a very nice transition state there. It can take this hydrogen off, and that is going to push those electrons over here, and those electrons will make that pi, and then the electrons here can go to the sulfur, and you get DMS that you say are the same thing in ozonolysis, right? Very similar to that. So here you are going to take this, and there's one hydrogen remaining. That's why primary goes to the aldehyde. And here is your DMS, sulfur. Got both your lone pairs back, and DMS is a very stable molecule. Here's your aldehyde. So this is a little long drawn because we have to make this active moiety in situ. So that means it happens while you add it, and then you dribble that alcohol into it slowly. And then while you dribble it in, it's just going to do this reaction, and it's going to give you a very nice aldehyde. And that's where we are going to stop, because we don't want to take this to a carboxylic acid. This is not powerful enough to oxidize this. So it stops there, right there. So primary goes to aldehyde and stops at aldehyde. We don't go to a carboxylic acid. So that's the very nice thing about SWERN and PCC. Those are the two that can go from primary to aldehyde. Jones will go all the way to carboxylic acid. And secondary will always go to ketone no matter what you use, because there isn't another hydrogen to take it further to an acid. All right. We'll see you soon with more reaction. Bye.